Lab 1. Constant Velocity Motion. This lab is to describe how to calculate, predict, and express an object moving at a constant speed in constant direction, known as constant velocity. To show an object moving at a constant velocity, I rolled a ping pong ball across a table. To analyze the motion of the ping pong ball, I use Tracker to assess what is happening. Here's the selection I used to analyze. The origin is placed at the ball's center of mass at the beginning of what I am calculating. The positive x direction goes toward the right, the same direction as the ball moves. For a reference measurement, I used the width of a ping pong ball, which is about 40 millimeters in diameter. The change in time of what I am calculating goes from 0 seconds to 1.102 seconds. To create a mathematical model of what is happening, I edited the program Lab1 Start and VIdle to the specific situation of my video. I made no change to the setup of the visualization and graph initialization. In the System Properties and Initial Conditions portion of the program, I input the ball's mass equal to 2.7 grams. The initial position where time equals 0 is close to 0 meters in the x-coordinate and is 0 for the y and z coordinates. The average velocity is 0.402 meters per second in the positive x direction, which is found by the change in position over the change in time, delta p over delta t. To match the tracker program, I input the starting time at 0 seconds. The model is set to predict the ball's position for 1.102 seconds. In the model, in order to have a constant velocity, the net force is assumed to be 0. Inputting the net force of 0 into the model leads us to see that the final velocity is equal to the initial velocity, meaning that it is constant. If we run the module, we see that the ball moves in the positive x direction in the visualization and increases in position in the graph. If we input the data from both of the programs into a data sheet that looks like this, we will end up with a graph that looks like this. In this graph, we see the experimental position of the graph varies from the model position. This is because while we assume no forces were being acted upon the ball, forces like gravity, friction, and air resistance were unable to be controlled in the physical experiment. What do I mean when I say that those forces act upon the ball? Those forces slow down the ball, decreasing the velocity. What if the mass of the ball was changed in Python? Because the net force is equal to 0, it would lead to no change in the outcome. The final velocity would still equal the initial velocity.